Welcome to today's explainer. Whenever I look at one of those massive industrial facilities, like towering chemical refineries, power plants, or water treatment centers, I always wonder, how do they actually know it's safe to turn the whole thing on? We're talking about miles and miles of interconnected steel here. Just one faulty connection, and the consequences could be absolutely disastrous. So today, we're demystifying the ultimate stress test. It's the absolutely crucial process that keeps these mega facilities safe before they ever see a single drop of active product.
Okay, let's dive into this. Seriously, think about it for a second. How do you guarantee a massive industrial system won't leak or explode when it's finally filled with high-temperature, highly hazardous chemicals? The stakes of plant construction are astronomically high. You can't just cross your fingers, flip the switch, and hope the builders did a good job, right? You need definitive, undeniable proof that the physical integrity of the plant is flawless. Basically, you need a way to push the entire system to its absolute limits, safely. To wrap our heads around how engineers achieve this seemingly impossible task, let's picture something super relatable. Imagine you've got a flat bicycle tire, and you're trying to find that tiny, practically invisible leak. What do? Well, you pump the tire full of air, submerge it in a bucket of water, and look for the bubbles. Now take that exact same foundational logic, but apply it on a massive, heavy-duty industrial scale. We're doing the exact same conceptual thing, just with incredibly thick materials and astronomically higher forces.
Which brings us to the core of today's explainer, the hydrostatic test. This is an absolutely crucial safety procedure. Its entire purpose is to verify that the piping and the welding connections can withstand their designated maximum pressure without leaking even a single drop. And notice I'm emphasizing those words: piping, welding, and pressure. In plant engineering, a pipe is truly only as strong as its weakest weld. So this test is essentially the final uncompromising exam for every single welder who worked on the site.
Now, you might be wondering about the testing medium itself. Like, why use water? Why not just pump the pipes full of high-pressure air like we do with that bicycle tire? Well, this is a really fascinating safety detail. We use water because water is practically incompressible. If a weld fails and a massive pipe ruptures during a water test, the pressure drops instantly and the water just spills out onto the ground. Sure, it's a giant puddle, but it's safe. Air, on the other hand, it's highly compressible. If you compress air to incredibly high pressures and a pipe bursts, that rapidly expanding air turns the pipe into a literal bomb, sending dangerous shrapnel everywhere. So water is a strict industry standard. It stays predictable and, most importantly, safe under extreme pressure. So the crucial point is understanding exactly what we are testing when we're out on the construction site. You might assume we test the entire plant, the machines and the pipes, all at once. Actually, scratch that, we don't. The giant pieces of machinery, like massive pressure vessels and fluid pumps, are all fully tested back at the vendor shop. That's the factory where they were built. The manufacturers do their own intensive hydrostatic tests before the equipment is ever loaded onto a truck. Therefore, when we are on the actual construction site, our hydrostatic test is strictly focused on the piping, that newly welded vascular system connecting all that factory-tested equipment together. Now, what's really interesting is the physical hardware engineers use to set this up. Since we're only testing a specific section of piping and not the machinery it connects to, we have to isolate it. To pull this off, they use a solid metal plate squeezed tightly between two bolted rings. Those outer rings are called flanges, and that solid metal plate sandwiched right in the middle is appropriately called a blind. It literally blinds or blocks the path of the pipe. By bolting blinds into the flanges at both ends of a piping section, engineers create a temporary, completely sealed chamber. The fluid can't escape into the main equipment. It's perfectly trapped exactly where we need it for the test.
Let's move to and see how this builds into the actual testing procedure out in the field. It's a very methodical four-step process. First, the team installs those blinds we just talked about to completely isolate the target section of piping. Second, they fill that isolated section entirely with water, making absolutely sure every little bit of trapped air is vented out. Third, using a specialized pump, they gradually increase the pressure inside the pipe to a very specific target level. And this level is usually significantly higher than what the pipe will face during its normal daily operations. We really want to overstress it, just to be sure. Finally, step 4. They stop the pump, hold the pressure, and monitor the whole system.
And honestly, that holding phase, that is where the tension on a construction site really peaks. You are literally waiting for the drop. The engineers stare at highly sensitive pressure gauges for a set period of time, which can sometimes extend for hours. If the needle on the gauge holds perfectly steady, boom,
The test is a massive success. The structural integrity is verified and the welds are flawless. But if that needle starts to creep downward, even by a tiny fraction, your heart sinks. A dropping needle means there's a leak somewhere in that vast maze of steel or some loss of pressure, and the meticulous hunt begins to find out exactly which weld failed.
Section 1. The cost of rework. The domino effect.
All right, let's look at what happens when mistakes made much later in the assembly process suddenly invalidate the test we just worked so incredibly hard to pass. Picture this scenario. The hydrostatic test for your piping section is perfectly complete. The plant is smoothly moving into final assembly. But then the installation team discovers a simple misalignment. The flange on the massive rotating fluid pump doesn't quite line up with the flange on the piping we just tested. We might be talking about a difference of just a few millimeters here. But remember, these are rigid, incredibly heavy industrial steel pipes. You can't just bend them into place with sheer force without completely damaging the equipment. A tiny spatial misalignment here can literally undo weeks of hard work.
And this brilliantly illustrates the brutal reality of plant construction. Because you can't simply force the alignment. What's the actual timeline to fix it? Well, first, you have to bring in tools to literally cut the newly installed pipe flange off. Second, you have to realign everything perfectly and perform brand new welding to reattach it. But here is the massive kicker. Because you just introduced a brand new weld into the system, step 3 dictates that you must completely repeat the entire hydrostatic test for that entire piping section. All the blinds, the water filling, the pressurizing, the agonizing waiting, the whole shebang has to be done again just because of one slightly crooked connection.
Which leaves us with this final, kind of mind-blowing thought. If a single misaligned flange can trigger a massive, incredibly costly retest that delays the entire project and burns through thousands of dollars, just how critical is microscopic precision from day one? It completely reframes how you look at these enormous industrial plants. They aren't just brute force constructions of heavy steel, they're absolute masterpieces of exact, careful engineering, validated drop by drop under immense pressure. Thank you so much for joining me on this explainer. Keep questioning how the complex world around you is built, and I'll catch you on the next one.